The 11th in a series of videos where we look at various compounds to determine if they are acids, bases, or salt solutions that, when dissociated in a soluble aqueous solution, the ions will continue on and hydrolyze and act as acids or bases in solution. We have identified the characteristics of all of the molecules that have been crossed out on this page so far, and we're currently focusing our attention on compounds with hydrogen in the center of the formula. So we're going to look at these compounds here which contain carbonates, as well as here the bisulfite ion, and also this ion here that is called the monohydrogen citrate ion, and I'm going to show you how they will all be treated the same way. When sodium bicarbonate dissolves in solution, it 100% dissociates to form 0.5 molar sodium ions in solution, but those are spectator ions and they will not hydrolyze. So they will not alter the pH of the solution. However, the bicarbonate ions have the ability to act as either an acid or a base. It is an amphiprotic ion, meaning that it can take up a proton to turn into its conjugate acid, or it can give off its remaining proton to turn into its conjugate base. We can see here that the bicarbonate ion is listed as a base with its conjugate acid having a Ka value of 4.3 times 10 to the negative 7. So we can use that value to calculate the Kb value for the bicarbonate ion, and we will determine it to be 2.3 times 10 to the negative 8. Remembering that we calculated this value by taking the K value for water, 1 times 10 to the minus 14, and dividing by the K value for its conjugate acid. We also see bicarbonate later in the table shown as an acid, and its Ka value is given here. So now we can compare the Ka value of that bicarbonate ion to the Kb value of the bicarbonate ion that we calculated above, and we realize that the Kb value is much greater and that the bicarbonate ion will act as a base. That's not a surprise to biologists when we talk about bicarbonate in digestion and bicarbonate buffers later in the course as well. I won't spend much time here reviewing how to solve the ice grid, as we've done many calculations that look just like this, remembering that we are recognizing that this amphiprotic ion, because it has an ionizable hydrogen and yet it has the ability here with the negative charge to accept a hydrogen, we're recognizing that we've identified that its Kb value is higher, so we're setting up our ice grid to solve for X, which represents the amount of hydroxide which is released into solution when that bicarbonate ion hydrolyzes. My answer is a pH which is basic as expected. You can treat the other examples the exact same way that you saw in our chart before. So we know that this is just another example here of a bicarbonate compound. We'd have a similar solution that would play out for this compound. But the last one I want to take a look at here is the example shown at the top right here. We've seen several examples of compounds with cations that do not hydrolyze attached to amphiprotic ions that have an H at the front and a negative charge, which indicates that they are either the result of an acid ionizing already, or they themselves could ionize as an acid and turn into its conjugate base. So amphiprotic, meaning you'll find it two different times at the table, on the table, once labeled as a base, once labeled as an acid. Why don't they list what the ion was at the front of this molecule? One possible reason is, why mention a spectator ion that we already know is not going to affect the solution or change its pH? And so in an effort to be efficient, they don't even add the spectator ion on there, as it won't change our answer. So we can treat this just like the other examples at the start of this video. We would compare the Ka value of that monohydrogen citrate ion here with the Kb value that we would have to calculate using this value. Keep in mind, it is a really common error for people to use the incorrect Ka value in this calculation. So make sure you're understanding why I'm looking for this value to be used in the calculation of this ion's Kb answer. When I compare the two answers together, I can see that the Ka of the monohydrogen citrate ion is much larger than the Kb, and so therefore I can conclude that this will have a pH less than 7. This will be an acidic solution. If I wanted to, I could go on and set up ice grids and solve for an exact pH. And so don't be afraid of amphiprotic ions that you see several times in the table. You can treat them the same way as you can those salts that show the cation in front of the compound.